Hello everyone, my name is Dmitry Khomchenko. Welcome to my presentation about the transmission-aware multiple Lightpath reconfiguration in Flexgrid Optical networks. Before starting, I would like to thank my co-authors for their available contributions. Here is the outline. At first, I'll give an overview of the problem, then I'll explain constraints and the objective function. I will present the workflow of our algorithm and present exemplary simulation results. Finally, I will conclude the presentation. Elastic optical networks that utilize FlexGrid and bandwidth variable transceivers require effective lightpath reconfiguration, so traffic growth and route failures can be addressed. It is critical that this reconfiguration uses the available spectrum and provides feasible quality of service or quality of transmission line. To accommodate the traffic growth, the existing route can be reused, but the available spectrum should be larger than the signal bandwidth of the reconfigured bandwidth variable transceiver. It might happen that the existing route doesn't offer enough frequency slot or that it is broken. Then alternate routes must be found. Here, for instance, two alternate routes exist. The ABC link offers two spectral windows marked as red and blue, while the ADC link has only one frequency slot that fits. So we have three alternate light passes to choose from. Also, we should keep the quality of transmission line in mind. Alternate routes are usually longer, so they require more amplifiers and, consequently, have a higher OSNR degradation. And we should make sure that the available frequency range fits the channel bandwidth, which depends on the updated bandwidth variable transceiver configuration. So it is bitrate and modulation format dependent. And finally, the impact of cross-channel interference needs to be considered. Since optical channels are placed closely in FlexGrid networks, the impact of nonlinear noise on quality of service is essential. So the question is, how to reconfigure one or several light passes in an optical network and account for the requested traffic growth, available frequencies and alternate routes, the receiver sensitivity and GSNR degradation, and potential frequency conflicts which appear when several light paths are reconfigured at a time. Now let's formulate the constraints of our algorithm. First of all, we need to select good quality of service measure. We picked the receiver OSNR threshold because the required power level can often be achieved by adding more amplifiers. We use FlexGrid applied to C-band to calculate available frequency ranges, but the algorithm itself is flexible enough to support either flex or fixed grid and other transmission bands. We calculate the generalized SNR degradation caused by ASC and nonlinear noise and compare it with the receiver sensitivity. And we consider networks with various transceiver configuration. Depending on the bandwidth variable transceiver configuration, the required bandwidth differs. So this imposes an additional constraint on the research of alternate routes. And of course, we account for the two classical constraints for lightpath rerouting. Keep the same set of frequency slots assigned to a light path along the road and avoid overlapping with other light passes. We compare two models for estimating the OSNR degradation for any light path. First, each fiber span along the road adds loss, which is compensated by amplifiers while noise is added. The approximate model assumes exact span loss compensation by variable gain amplifiers after each span. Additional assumptions are made about the amplifier noise figure and loss of a drop equipment along the route. The problem is that the post-compensation of loss always overestimates the OSNR degradation compared to a booster plus preamplifier scheme. The exact model, on the other hand, accounts for the detailed equipment configuration. It includes not only add drop equipment loss and booster amplifiers, but also frequency-dependent parameters such as fiber loss and amplifier gain. The target of our algorithm is the minimization of GSNR degradation introduced by reconfigured light paths under the constraints and model assumption discussed before. In other words, we select the route and allocate frequencies that minimize the GSNA degradation due to amplifier noise and cross-channel interference. The different steps of the Lightpath reconfiguration algorithm are designed as a part of general-purpose network design environment. It allows you to configure a network from topology definition via equipment configuration to performance assessment. Once you have configured the network, you might consider Lightpath reconfiguration scenarios. After that, the feasibility of the network should be rechecked. Let's have a look at the individual states of our algorithm. The network data, including fiber span parameters and equipment parameters, are read at the first step. Other input includes information about existing light passes and, of course, the list of light passes that should be reconfigured, along with the new configuration of the corresponding bandwidth variable transceivers. The car-shortest path algorithm is then used to find alternate routes that meet the constraints. The route should provide enough frequency slots to accommodate the requested bandwidth. OSNR should not go below the receiver sensitivity plus margin. We use 3 dB here. The search stops when 3 alternate routes are found. The calculated routes are sorted by OSNR in descending order. Eventually, we calculate candidate light passes, which may differ by available frequency slots. All candidate light passes are then sorted by their available spectrum range. The next step is essential for multiple light path reconfiguration. Here we generate the list of combination of candidate light passes that should be assessed later. Then, the frequency conflict matrix is built for each combination. At this step, the combinations are sorted with respect to OSNR and available frequency slots to have combination of light passes with high OSNR and broader available spectrum ranges at the beginning of the list. As this step is time-consuming, we stop the analysis when the first combination in the list remains unchanged for 100 analyzed combinations. Once the conflict matrix for combination and the available slots for each candidate light path in the combinations are known, the algorithm allocates frequencies. Having defined all parameters of candidate light passes, after frequency allocation, we can now calculate nonlinear noise and GSNR and the rank combinations with respect to quality of transmission line. We define the highest GSNR penalty as combination weight. It is calculated as the difference between OSNR and GSNR in dB units for each candidate light path in that combination. The combination with the lowest weight is considered as the solution. The last step of the algorithm is to reconfigure equipment in the network to deploy the solution. That is, bandwidth variable transceivers and WSS ROADM connections along the new light passes are updated. Let's see how the algorithm performs. At first, we check the feasibility of our nonlinear calculation by comparing it with the results published earlier. We simulated 3 subnetworks with 14, 17, and 15 nodes of German topology. Here are the specs of the 14-node network, and here of the 15-node network. The investigated topologies have different numbers of spans, repeater hearts at drop nodes, and light passes. We compared simulation time for different numbers of light passes that should be reconfigured at the time in the 3 subnetworks. And of course, we compared the accuracy of the approximate and exact models discussed above, using a 17-node configuration of a German topology depicted here. It has been widely used in recent years to test planning algorithms. First, a few words about the feasibility of the algorithm we present here. We calculated the OSNR using the approximate and exact models and compared the simulation results with values calculated in our network design environment. Its feasibility has been tested and verified in our previous works. We found that the underestimation of OSNR and GSNR using the approximate model is more than 1 dB on routes with several intermediate nodes. On the other hand, the exact model delivers predictions in a good agreement with the reference models. This is an underestimation in the approximate model strongly affects the Lightpath reconfiguration, which we will present later. Simulation time depends strongly on the number of light passes to be reconfigured and is quite similar for all three subnetworks used in simulations. A longer time for more light passes to be reconfigured is expected. A problem, however, is the significant growth of simulation time at the increase of light passes in question, when candidate light passes share available frequencies ranges. It is impossible to simulate separately smaller subgroups of light passes in such a case. As a result, the number of combinations to be analyzed becomes very large. Currently, a lot of time is wasted because the conflict matrix is recalculated for each light pass combination. Our preliminary estimates show that simulation time reduces significantly by pre-calculating the conflict matrix. Now, a few words about the algorithm accuracy and efficiency. We show here results of reconfiguring the 10 longest light passes in the network. The OSNI and GSNI values after light pass reconfiguration agree with the reference model when using the exact span loss calculation model. On the other hand, the approximate model underestimates the OSNI and, as a result, the GSNI values. So consequently, the algorithm did not find alternate passes for 5 of 10 light passes with the approximate model. So in Flexgrid networks with colorless, directionless, and contentionless configuration of add-drop nodes, it is crucial to estimate quality of transmission line accurately. The exact model should be used, or an adaptation of an approximate model is required. So let's summarize. We have presented an effective multiple light pass reconfiguration workflow. It accounts for linear, so non-linear degradations of a signal along the links. And it is flexible enough to support conventional fixed grid and flex grid networks in a single or multi-band transmission scenarios. Our presented algorithm supports multiple light pass upgrade with respect to traffic growth and for path restoration. In the future, we plan to enhance the algorithm, for example, by reducing the simulation time and spectrum fragmentation. Thank you very much for your attention. Please feel free to contact me for questions and comments.